today about the root locus model for an aerator mixer system. I'm going to be talking about the aerator mixer station here in Chattanooga and the previous work that we've done so far as a group. I'll tell you about the root locus theory and modeling, the results analysis that I got from the root locus plot, and some conclusions that I drew from the model. A little background: this is our system. It is a feedback control system with a speed transmitter, a controller, and a speed actuator that turns the gearbox, which gives a certain speed to the mixer. And this is a block diagram of our system with the input as a percentage and output as RPMs. This is the steady state operating curve for our system with an operating range from 10 to, well, it's actually 70 RPMs to 1700 RPMs. And this is an example of the step response curve showing the dead time, gain, and time constant. This is the model fit for that same plot. And here are the step response results with a gain that's pretty consistent throughout the board. And the dead time is fairly consistent. It ranges from 0.11 seconds to 0.159 seconds. The first order time constant, it varies a little more from 0.15 to 0.21 seconds. This is the transfer function of our system, with the gain is 17.75 RPMs, the dead time of 0.11 seconds, and a time constant of 0.23 seconds. This shows your input as R of S with your output as C of S. And the GC of S is your your control function, and the G of S is your transfer function. And this is a time response with a sine input that shows your period, your amplitude, and your phase shift. So you can get your amplitude ratio of 12 RPM per percent and your phase angle of 51.3 degrees. And you can use that to form a buddy plot. This is for the lower region, which is 10 to 40% input with your gain, your order, ultimate frequency, and your ultimate controller gain to that region. This is your middle region, which is from 40 to 70%, which gives you the same information. And this is for your upper region. And here's the buddy results. The gain again is fairly consistent from 17.75 to 18. The order for the first two were 1.5, and for the upper it was 2. And the ultimate frequency for these results, it goes between 1.8 hertz and 2.4 hertz. And this is the ultimate gain of the controller. It seems to increase steadily from 0.15% per RPM to 0.32% per RPM. And this is the input function for the time response, which is a sine function. And these are the two model equations for your amplitude ratio and your phase angle. And this is the Bodie model, which for all three curves, it shows you your model gain, your dead time, and time constant. Here's the results. You have a steady gain throughout the model at 17.75 RPM per percent. The dead time is longer for the lower region than the upper and middle regions. And the time constant increased steadily as the input increased. And this is the theory for the root locus modeling. For a proportional feedback controller, the controller transfer function is equal to the controller gain. And using this information, the closed loop transfer function can be determined and the characteristic equation can be determined. The roots of the characteristic equation are the points that make up the root locus plot. And the root locus plot is used to find several controller gains that give you different responses to a step change in the set point. And these different responses are, the ultimate controller gain, and then quarter delay, a tenth delay, 5/100 delay, decay, critical dampening, and then the range for your underdamped responses and the range for your overdamped responses. For our feedback control system, this is where your controller gain it replaces your controller transfer function, and this shows the closed loop transfer function, and then derived from that is just the denominator, which is your characteristic equation. And here's the root locus plot for the lower region for the speed system. It's used to find the ultimate controller gain, the controller gain at quarter decay, tenth decay, 5/100 decay, and then for critical damping. And this is for your middle region. This is the upper. Then again, they all have almost the same gain with a slightly different time constant and dead time. Here's your results for the lower region. It shows the ultimate controller gain at 0.22% per RPM. Your quarter decay has a KC of 0.15. Tenth decay is 0.14 and decreases to 0.13 for your 500 decay, with your critical damping at 0.01% per RPM. So with that critical damping, you have your underdamped range with any controller gain above 0.01, and overdamping would be any controller gain less than 0.1% per RPM. This is your middle region. Within it, there again, you're decreasing controller gains as you go from quarter decay to 500 decay, with your critical damping at 0. So your underdamping response, or your underdamping range, is any controller gain below or above 0, and your overdamped is any controller gain above 0. This is the upper region. It has the same critical dampening as the lower region. And as the summary here, you can see the lower region in red, the lower region in green, the middle region in red, and the upper region in blue. And for the ultimate frequency, you're the exact same for your middle and your upper range, and you're slightly higher on your lower region. The quarter decay varies a little much. It seems that for the quarter decay, tenth decay, and 500 decay, that the middle region is lower in relative to the lower and upper regions, and also with the critical damping. And this is just a plot of the root locus versus the Bodie results that we got, and I saw it to be quite interesting that the lower region for your Bodie is smaller than the middle or the upper region, but it goes the opposite direction for the root locus. And that's it.
Could you go back